In this video, we want to look at Newton's method. And Newton's method is a way to find zeros of a function. And this method is an approximation. This is actually the method that your calculator uses to find zeros when you want to find zeros. So we want to kind of show how this works, kind of use the calculator to maybe help us do some of the calculations, but to show you kind of what's going on in the background. Now, before we get to Newton's method, I want to look at a different method that is more straightforward. It is easier to understand how to do it. It's just very time consuming. So let's imagine we want to find the roots of x squared minus 5. Now, I know we can do that. We all know that that root is the square root of 5. So we know that. Now, let's say, though, that we want to try to find what is the square root of 5. We don't know what that is. So this is also kind of be considered a method for how could you approximate what the square root of 5 is. So what we're going to do is we're going to start off looking at some numbers. And I'm going to kind of do one example of this, and then we'll kind of go quickly and just kind of write down the numbers. So imagine I take 2.5 squared minus 5. So I put 2.5 into our equation, and I get 1.25. So if I do that, I get a positive number. If I put in 2 squared is 4, minus 5, negative 1, I get a negative number. So I know that my answer has to be between 2 and 2.5. So I'm going to go the bisection method. I'm going to go in the middle. So I try 2.25. If I put 2.25 into the calculator and did the same thing, and this is where I'm going to go quickly and just kind of write down the answers, I would get a positive. Now, if I then go in the middle of that, this is 2.125, and I get a negative. And to speed this up, I'm just going to write this down. And then if I go in the middle of that, I get 2.1875, and that's a negative. I now, between the negative and the positive, if I go in the middle here, I get 2.21875. And just to reiterate what I'm doing here, I am going 2.5 plus 2.1875. I'm dividing that by 2. And I did not get what I should have gotten. What did I... Oh, I used 2.5. Sorry. I should have used 2.25. So let's try this again. I have 2.25 plus 2.1875 divide by 2. That gives me my 2.21875. If I now take that answer and square it and subtract from 5, I get a negative, which tells me that's a negative. So now I go again between these two, and I get 2.234375. And if I do that, I get a negative. And then if I go between that, I get 2.2421875. And if I put that in, I get a positive. So what we now know is between these two numbers. So we know the square root of 5, whatever it is equal to, is between 2.234375 to 2.2421875. And I think you can see how we could continue doing this over and over and over again. And the further we go, the more decimal places we could get. But we have now found an approximation for what the square root of 5 is. So that's bisection method. That's kind of just going guessing. That's not necessarily guess and check. There's a method to it, but you're just kind of going in the middle and kind of working your way in to get this. Newton's method is going to be a faster, better way. And notice, we got that accurate without even knowing how to find the square root of 5. All we were doing is dividing by 2, squaring it, subtracting 5. Okay? So, let's talk about how Newton's method works. So what Newton's method does is, let's consider this picture here. We're going to start at some point here, x1. This is the initial guess. Think about when you do these on the calculator, it asks you for a guess to start your problem. Now, once you find this point to start, you are going to find the equation of the tangent line. And we know how to do that. That equation, sometimes called a linearization, that equation of the tangent line is just the derivative at x1, and then our point slope form with the functional value at that line. So we find that line. Now, once we find that line, we then, this is in line, that's simple math, we then find that line where its x-intercept is. And you can see it's moved closer. That gives us this next functional value point. From that point, we are going to find the slope of the tangent line again. That x-intercept here is going to give us a new point, x3, and that's going to give us a new point on our function. And now we're going to take that new point on our function to there, find this new point, which is x4, and you see we just going to continue and continue in, getting closer and closer approximations to our root. Now, let's kind of look at the procedure for doing this. So first, you are going to guess x1, maybe given x1. Okay, as a solution to our function. Then you're going to find the linearization. So that linearization, as I just said, would be f prime of x1 times x minus x1 plus the functional value at x1. That's just a linearization is just fancy word for the equation of our tangent line. Then we are finding the x-intercept of our tangent line, our linearization. We're going to make that x2, and then we're going to repeat. Going to go back up to the top, do it again, and find that. Okay. Now, if we think about our linearization, so here is our linearization for x1, and I want to find x2 that makes this 0. So I want to find this x2 right here that makes this equal to 0. Now, this is a linear equation, so I can just subtract this over and divide, which would give me x2 minus x1 is going to give me minus f of x1 divided by the derivative at x1. And then to find x2, I just add the x1 over, and I get minus f of x1 all over f prime of x1. Now, if you could imagine for a second that we then do the same thing with the x2, and we get our equation of our tangent line at x2. We set it equal to 0 to find our x3. The same pattern. I think you can see that my x3 is going to be almost the same thing, and so forth. And then x to the 4, and so forth. So what this leads to is this formula for Newton's method, where if we want to find the second term, we just put the first term into this formula. The third term, we put the second term in, and so forth. Okay. So let's do an example. Let's go back to our x squared minus 5. So first, my derivative is 2x. So my formula, and I'm going to write my formula over here. My formula, and let's not even use that. So let me change this here. If we have x2, would be x1 minus x1 squared minus 5 all over 2 times x1. So now, let's say our x1 is 2.5. So my x2 would be 2.5 minus 2.5 squared minus 5 all over 2 times 2.5, which if I did that will give me 2.25. Now, if you look back up to our original binomial method, you could see we're to this same value. We went from 2.5 to 2.25, not much different than we did the bisection method. Now, let's find x3. This would be 2.25 minus 2.25 squared minus 5 all over 2 times 2.25. And this is all just throwing stuff in the calculator. We're speeding it up here by not going through the calculations. And I have 4 ones. So I get to there. Now, already 2.236, if we go back to our bisection method, you can see already we're at 2.236 already. And if we look at the square root of 5, because as soon as we can see 2.236, we are already, after 2 times, already closer than we were after a whole bunch of work with the bisection method. So Newton's method quickly gets us to a really good approximation. Now, if we want to get closer, we could do it again, and we could find the fourth, and so forth. Now, let's look at a way we can make this go quicker by using our calculator. Okay, so here's how we're going to do this on the calculator. We're going to use the answer button. So we're going to start off by putting our initial value in, 2.5. And then our formula from Newton's method is going to be x sub 1, which is my answer, minus my answer squared minus 5 divided by 2 times my answer. So if you look at that, that formula right there is this formula right here. And when I hit enter, I should get 2.25. Now, because I have used the answer button, if I hit enter again, I should get 2.2361111. And you can see we got that. So what we can do is just to do, there is the first term, the second term, the third term, the fourth term. Now, how do we know when to stop? I don't know what the square root of 5 is. If I knew what the square root of 5 was equal to, I wouldn't necessarily need to approximate it. So what I can do is hit enter again. And you will notice at this point, to 1, 2, 3, 4, 5, 6, 7, 8 decimals, my answer is exactly the same. So you can hit enter until you see that nothing changes. If I hit enter one more time, there is my answer. 2.236067977. Now, you also could just say, well, that's just the square root of 5, and therefore I know the answer. Yes, we know the answer before we start. That's what the calculator is doing for us, but this is the process it goes through. So one of the things when we do these problems, we will say, hey, write down the first 4 numbers. So it's not just the final answer that we want, but it's understanding the process of how to get there. So let's look at another example. Let's say we have this, x cubed minus x plus 2 equals cosine. Now, the first thing, for Newton's method to work, we have to set this equal to 0. So we are going to get x cubed minus x plus 2 minus cosine is 0. The second thing we need to do is we need to find our formula. So our formula is x minus our function on the top divided by the derivative, which is 3x squared minus 1 plus sine of x. And I'll just give us our starting point of -1. So now let's go to the calculator. So we start off by putting our starting point in. Our formula is answer minus, once again, make sure you are in radians for this, minus answer plus 2 minus cosine of my answer, divide by 3 squared minus 1 plus sine of my answer, parenthesis, parenthesis. And if I hit enter, I get negative 2.259957822. We could write that down. That's my second term. My third term is negative 1.769444. Write down the first 6 or 7 terms. There's my third. There's my fourth. There's my fifth. You know, it's still changing. There's my sixth, still changing. There's my seventh, still changing. There is my eighth. So finally on my eighth term, before it changed, so my eighth term is negative 1.51129747. And we could write down, I have them written down here, my second term is that. My third term is this. So as you do these, it will say, write down the first couple terms to kind of show what they are, and then end up at what the final is. Now, if you were not given a first term, how can you find a first term? Well, one way to find a first term is to go back to your calculator and to graph this. So if I graph this function, minus x plus 2 minus cosine. And I graphed it. I could say we picked, it's between -1 and -2. So my initial guess was -1. So you may use the graph. Now, the graph also brings up some questions, though. If we think about this tangent line as being our intercept, there are problems we can get with this. So some of the problems we can have is, one, if we look at the first one here, and we don't have a 0, our function just gets really, 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 really close. It may never get to a point. Or it may get to a point that's really the minimum and is not a 0. That's one problem. Another problem you can get is something like natural log. Is, let's say I start at this point and the slope of my tangent line is over here. My function is now undefined. So as I go to find the derivative and the functional value of all that stuff at -1, I get an error and the whole thing doesn't work. Okay. That's one of the reasons on the calculator they always say put these little arrows to show you where your answer is, and then start with a guess to help you narrow it down. That also leads to the other problem. It's possible you may have more than 1 0. So you may start with a point. You are going for this 0 right here. You start with a point here. It actually comes over here and finds this 0. So those are all problems that when the program on your calculator has you put these left and right bound to try to narrow down some of these mistakes, it has a little bit more kind of fail-safe things in it that can deal with some of these kind of problems that we are not looking at. All right, that is 4.8, Newton's method. You can now do the homework.